Hello and welcome to Science Night Tales. I am glad you have found this quiet moment to look up. Tonight we are going to trace a very old path, the one that leads from the ground beneath our feet to the stars above our heads. We often think of astronomy as a science of telescopes and equations, but it began much simpler than that. It began with eyes, patience, and the quiet realization that the lights in the sky were not random. We are going to follow the long lineage of people who watch the night, from the first stone circles to the backyard telescopes of today. We will see how our view of the universe grew larger, deeper, and more beautiful with every generation. You do not need to memorize constellations tonight. You can simply let the rhythm of the sky wash over you. The stars are steady, the night is calm, and you are safe to drift. If this perspective helps you feel connected to the vastness, you are welcome to like or subscribe. For now, let go of the day and let's watch the sky turn together. Consider this. When you look up at the night sky, it appears dark between the stars. A simple observation, one most people accept without question. The stars are there, pinpoints of light against the black, but between them lies this quiet darkness. It feels familiar, almost comforting in its stillness. Yet this very darkness holds a key, a quiet, patient key to understanding the entire structure of the universe, its true age, and even the nature of what we call empty space itself. What if I told you that explaining something as everyday as why the sky turns dark at night required centuries of gentle, persistent human effort? From the earliest models that pictured the stars fixed on an enclosed celestial shell, all the way to the modern understanding of expansion, of origins, of a beginning. This video essay simply explores that long, quiet journey. It reveals how we, from our small, limited place on Earth, have slowly pieced together the scale and the shape of the cosmos around us. The thesis here is straightforward and perhaps a little humbling. The concept of nothing in space is not merely an empty void. It is a dynamic element, shaped by time, by immense distance, and by the finite history of the universe itself. By understanding this, we gain a clearer glimpse into reality at its very largest scales. Pause for a moment. Just breathe and think about the vast distances involved. The light from distant stars, some of them, takes billions of years to reach us. Billions. That light left its home long before our world even formed, long before the first quiet thoughts under the stars. And yet, it arrives now as a faint glimmer. All that journey through the dark creates this illusion of emptiness, an emptiness that gently challenges our everyday perceptions. This darkness is not just an absence, it is a consequence. It results from the universe having a beginning, a single quiet point where everything began to expand outward. Early thinkers, looking at the same stars we see, assumed something different. They pictured an infinite yet static space, filled evenly with stars in every direction. In such a universe, every line of sight would eventually meet a star, and the accumulated light from all those countless stars should make the night sky as bright as day, everywhere, glowing like the surface of the sun. But when night falls, it does not. The sky remains dark. That quiet mismatch, that gentle contradiction between expectation and observation became the spark. It drove generations of quiet curiosity, of patient observation, of careful rethinking. Discoveries that slowly redefined our place in existence. As we delve deeper, You'll notice how each small step built quietly on the one before it. No sudden leaps, just steady progression. From enclosed shells of stars to the realization of infinity, to the understanding that space itself can curve, can stretch, can evolve. The story begins, as so many do, with basic questions asked under starry skies. Questions children still ask. Questions adults sometimes forget to whisper again. Why is it dark up there? Where does it all end? And it ends, not with finality, but with quiet predictions. So predictions about a future far ahead where the expansion continues and more of the universe, bit by bit, becomes invisible to us. Galaxies drifting beyond the reach of light, fading into the same peaceful darkness we gaze at tonight. So, let us begin. Gently, by examining the foundations, the quiet assumptions, the early views, that set the stage for these revelations. There is no hurry. The universe has taken billions of years to reach this moment. We can take our time to listen, to reflect, to let the scale settle quietly into our thoughts. In the stillness between the stars lies not emptiness, but a story. A story written in light that traveled longer than we can easily imagine, arriving now to meet our eyes. And in that arrival, we find the first threads of understanding. Let us drift back now, slowly, to a time long before telescopes turned the night sky into something deeper than the eye alone could reach. Imagine standing on a quiet hill, or perhaps on the roof of a simple house, under a sky untouched by city lights. The stars are close enough to feel familiar, almost within reach. They move together, night after night, in slow, perfect circles around the pole star. The sun rises and sets, the moon waxes and wanes, the planets wander among the fixed lights. Yet everything seems ordered, contained, safe. This is the world most people knew for more than 1,000 years, a cosmos that felt small, enclosed, and centered on the place where human beings stood. At the heart of this picture stood the work of Claudius Ptolemy, a mathematician and astronomer living in Alexandria around the 2nd century CE. While Ptolemy did not invent the geocentric model, he refined it, polished it, made it match observations more precisely than anyone before him. In his great book, The Almagest, he described the Earth as motionless at the center of everything. Around it turned a series of transparent crystalline spheres, nested one inside the other like layers of an onion. Each sphere carried one or more of the wandering lights, the moon on the innermost, then Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally the great sphere of the fixed stars. These spheres rotated smoothly, at constant speeds, carrying their lights in perfect circular paths. When the planets appear to slow down, stop, and move backward across the sky, a motion we now call retrograde, Ptolemy added smaller circles, epicycles, upon the larger orbits. A planet moved along its epicycle, while the epicycle itself moved along the main circle. The result was complex but elegant. It fit the naked eye observations remarkably well. For centuries, this model explained the daily rising and setting of the sun, the monthly phases of the moon, the yearly wanderings of the planets, and the unchanging patterns of the constellations. It was not merely a scientific picture, it was a complete worldview. And because it worked so well for practical purposes, it became the reference point for everything that followed. Without this framework, later contradictions would have had no background against which to stand out. progress would have been slower, more disjointed. The model gave people a place to start, a map of the heavens they could trust. Pause here, just for a breath or two, or think how reassuring it must have felt to look up and see a universe that had clear boundaries, clear rules, and clear center. Us. Now consider the tools they had. No telescopes, no precise clocks, no photographs from space, only the naked eye, aided by simple instruments. The astrolabe, a beautiful brass disc with rotating parts that measured angles between stars and the horizon, used for navigation, for telling time, for surveying land. The quadrant, a quarter circle marked with degrees, held up to cite the altitude of a star. These were clever devices, but limited. They measured angles in the sky, not distances, so the stars appeared as points of light, all seemingly at the same distance, fixed like jewels on the inside of a great dome. The universe felt small, contained, almost intimate. The idea of true infinity, of endless space stretching forever, was rare, foreign, even unsettling to most minds. Most cultures, across continents and centuries, imagined the cosmos as bounded. In ancient Mesopotamia, the sky was a solid vault above a flat earth. In India, the earth rested on elephants standing on a tortoise beneath a layered heaven. In medieval Europe, the Ptolemaic spheres were woven into Christian theology. The fixed stars marked the boundary between the changeable earthly realm and the perfect, eternal, divine realm beyond. The shell of stars was not just astronomy, it was architecture of the sacred. Human beings stood at the center, not by accident, but by design. That centrality brought comfort, meaning, a sense of belonging in a purposeful order. It is hard, from our vantage point, to feel how deeply reassuring that picture was. Pause again. Let the thought rest. Now turn to the mathematics that quietly shaped how people pictured space itself. More than 300 years before Ptolemy, Euclid of Alexandria had written his Elements, a collection of definitions, axioms, and proofs that became the foundation of geometry for 2 millennia. In Euclidean geometry, space is flat, infinite in extent, but uniform in every direction. Parallel lines never meet. The angles in a triangle always add to exactly 180 degrees. These rules were not just abstract, they were assumed to describe the real space we live in. When ancient and medieval thinkers imagined the distance to the stars, they pictured straight lines extending outward, parallel lines staying parallel forever. Space was thought of as a simple, unchanging stage on which the spheres turned. No one seriously questioned whether space itself could bend, curve, or behave differently at great distances. Those ideas lay far in the future. In the background, another quiet debate had simmered for centuries. What about emptiness? What is the nature of the space between things? Aristotle, in the 4th century BCE, had taught that nature abhors a vacuum. A true void, he argued, could not exist. If a space were truly empty, nothing could move into it, because there would be no medium to carry motion. Motion required contact, a push. Therefore, nature fills every possible space. The heavens were filled with ether, a perfect, weightless substance. The region below the moon was filled with air, fire, water, earth. There was no room for true nothingness. Or this teaching matched what people could sense. Open a jar, air rushes in. Pump water from a well, air replaces it. No one had ever observed a perfect vacuum. So the idea persisted, aligning neatly with the picture of a cosmos without empty gaps, without true nothing. All of this, the spheres, the flat geometry, the rejection of vacuum, formed a consistent, comforting whole. It resisted change, not because people were stubborn, but because it worked. It explained what needed explaining. It gave meaning to daily life. And yet, even in this stable picture, small tensions existed. By the late Middle Ages and into the Renaissance, ancient Greek and Roman texts began to circulate again, brought back through Arabic translations, rediscovered in monasteries and universities. These scholars read Aristotle more carefully, Plato, even fragments of earlier thinkers who had imagined infinite worlds. Curiosity stirred, softly at first. In 1543, Nicholas Copernicus published his book on the revolutions of the celestial spheres, proposing that the Sun, not the Earth, stood at the center. The planets, including Earth, moved in circles around the Sun. It was a radical shift. But Copernicus kept the outer sphere of fixed stars. He did not remove the shell, he simply moved the center. The universe still felt enclosed, finite, bounded. The change was important, but incomplete. It prepared the ground, created a small crack in the old certainty. Psychologically, this is where the story begins to turn. Human minds tend to protect familiar patterns. When something does not quite fit, we often add small adjustments rather than rebuild the whole picture. That is what happened with epicycles. As observations accumulated, more and more epicycles were added, smaller circles upon circles, to keep the geocentric model matching the sky. It became very complicated, but it still worked. This is a quiet example of confirmation bias, the gentle human preference for preserving what we already believe, even when the system grows heavy. It delayed the shift to a new view, but it also kept astronomy alive, kept people measuring, kept the conversation going. All of these elements, the geocentric spheres, the flat geometry, the rejection of vacuum, the cultural comfort of centrality, the slow revival of ancient texts, formed the before. A world that felt ordered, enclosed, meaningful. A world that resisted vastness, because vastness felt lonely, uncertain, almost frightening. Yet science, at its deepest level, is iterative. It builds on what came before, even when it must eventually outgrow it. The enclosed picture held for so long because it was useful, beautiful, consistent with what people could see and feel. But usefulness has limits, and when small observations began to whisper that the shell might not hold, that space might be far larger, far stranger than anyone had imagined. The ground was already prepared for change, not sudden, not violent, but slow, patient, inevitable. So now, as we rest in this quiet understanding of what came before, we can turn gently toward what happened next, toward the first cracks, the first new lights that began to open the sky. And now, we turn, slowly, to the first gentle shift in that enclosed picture we held for so long. The year was 1572, a time when the night sky was still seen as unchanging, eternal, a perfect shell of fixed stars rotating quietly around us. But on a clear night in November, something appeared that no one expected. A new light in the sky, brighter than Venus, so bright it could be seen even during the day. This was a supernova, though they did not call it that then. They called it simply the phenomenon, an exploding star. far away in the constellation of Cassiopeia. To those who looked up, it must have felt like a whisper from beyond the shell, a quiet disruption in the order. The stars had always been fixed, unmoving, pinned to their sphere like distant lanterns. But this new light shone for weeks, then months, growing dimmer over time. It challenged everything. Pause here. Imagine standing outside on a cool autumn evening, the familiar constellations above, and then this unexpected glow. How it must have drawn the eye, night after night. Astronomers across Europe tracked it carefully. They noted its position, its brightness, how it did not move like a comet or a planet. It stayed fixed among the stars. Yet it changed. In the old model, the sphere of stars was thin, vast but enclosed, and nothing could appear or disappear there. Changes happened only below the moon, in the imperfect earthly realm. But this was above. It suggested the heavens were not so perfect, not so unchanging. Some sought explanations in faith. They whispered that it might be the Star of Bethlehem returned, a sign of something divine. Others saw omens, portents of trouble. The light was shocking, mysterious, troubling to the quiet order of things, and yet it sparked curiosity. In England, a man named Thomas Digges, a mathematician and astronomer, turned his gaze to this new star. Digges was not alone. He had a mentor, John Dee, a scholar and advisor to the Queen. Dee reasoned with him, quietly, that perhaps this was a moving star, approaching and then receding. Though that idea was wrong, it planted a seed. Digges began to question the shell. If stars could change, appear, fade, perhaps they were not all at the same distance. Perhaps the shell was an illusion. Let us breathe here, feel the weight of that thought. For centuries, the night sky had seemed like a dome close enough to touch. Now, one event, one quiet observation began to stretch it outward. Digges spent years thinking, observing, drawing. In 1576, he published his ideas, not as a grand treatise, but as a simple diagram added to an English translation of Copernicus's work. Copernicus had already moved the sun to the center, with Earth orbiting it, but he kept the fixed stars on an outer shell. Digges took that diagram and scattered the stars outward. No shell, just endless space. Stars extending infinitely up and out. He wrote of a sphere fixed infinitely up. Infinite, the word itself. Soft but vast. This was the first time in European thought that the cosmos was pictured without boundaries, without end. The mechanism behind this shift lay in something called parallax, or rather, the absence of it. Parallax is the way closer objects seem to shift position against farther ones when you move. Hold out your thumb. Close one eye, then the other. The thumb jumps against the background. If the stars were close, on a thin shell. Earth's motion around the sun should make them shift slightly over the year, but they did not. No parallax was seen. So, Digges reasoned, the stars must be immensely far away, too far for the shift to show. This simple lack, this quiet non-observation, pointed to vast distances, to infinity. Now, let us reflect on the methods they used. No advanced tools, just careful watching. Astronomers like Digges and Tycho Brahe, who observed the supernova with great precision, tracked its brightness day by day, week by week. They used instruments like the cross staff, a wooden rod with sliding crosspiece, to measure angles. They noted how the light peaked, brighter than any planet, then faded over 16 months. And crucially, its position stayed fixed relative to other stars. No daily parallax from Earth's spin, no yearly shift from orbit. It behaved like a star, but changed like something closer. This contradiction gently pulled at the threads of the old model. The implications reached beyond astronomy. Economically, better understanding of the stars meant better navigation. Sailors relied on star charts for long voyages. The Portuguese and Spanish were exploring new worlds, crossing oceans. Accurate positions of stars, even fixed ones, helped plot courses. But if stars were infinite, scattered at varying distances, charts might need rethinking. Trade routes to the Indies, to the Americas, depended on celestial navigation. A shift in cosmic view could quietly improve maps, reduce risks at sea, open new paths. Psychologically, the change was deeper. The old shell was comforting. It enclosed us like a great cosmic room. We were at the center, protected. Infinite space removed that. We became suspended in endless dark, a speck among specks. That evoked unease, a quiet isolation. Some resisted. Infinity felt too vast, too empty. It raised questions. If space is infinite, why is the night dark? But that paradox, Olbers' later name for it, was already whispering. Digger's diagram was a quiet revolution. It did not spread like fire. It seeped slowly into minds ready for it. Over the next centuries, it prepared the way for more. For now, in this chapter, we rest with that first opening. The shell cracked gently by a single bright light in 1572. And from that crack, the universe began to expand in our understanding. So let us pause, breathe, and carry this quiet shift forward to the paradoxes it birthed. We have arrived, gently, at a moment where the universe begins to feel too large. The shell has cracked open. Thomas Diggers has scattered the stars into endless space, no longer enclosed, no longer bounded, infinite. And with infinity comes a quiet question that refuses to fade. If the universe is infinite and filled with stars forever, why is the night sky dark? This question, first whispered by Diggers himself, would echo through the next 2 centuries. It became known later as Olbers' Paradox, named for the German astronomer Heinrich Wilhelm Olbers, who sharpened it in 1823. But the heart of it was already there in the late 1500s. Let us sit with it. Slowly. Imagine an infinite space. Static, unchanging, eternal. Filled evenly with stars, shining forever. Each star pours out light in every direction. Now, stand in any place. Look in any direction. Your line of sight stretches outward forever, because the universe is infinite and the stars go on forever. Every line of sight must eventually strike the surface of a star. No matter how far you look, there is always another star farther out. The light from all those stars, overlapping, piling up along every direction, should make the sky bright everywhere. As bright as the surface of the sun. Daylight all night long. No darkness, no black between the stars. Yet, when the sun sets, the sky turns dark. Quietly dark. That gentle contradiction, that soft mismatch, is the paradox. Pause here. Just breathe. Feel how strange it is. The logic seems perfect. Infinite stars plus infinite time plus unchanging space equals bright sky. But the sky is not bright. Something, somewhere, is missing. For nearly 300 years, from Daiges in the 1570s to the early 1900s, thinkers circled this question. They did not rush to solve it. They lived with it, turned it over in their minds, like a smooth stone in the hand. Most early models simply ignored parts of the problem. They assumed the stars were not truly infinite in number, or that space thinned out somehow, or that distant stars were dimmer in ways that cancelled the light. But none of these fixes felt complete. The deeper issue lay in something they had not yet fully grasped: the finite speed of light. Light does not arrive instantly. It travels slowly by cosmic standards, at about 300,000 kilometers per second, in an infinite universe that has existed forever. Light from infinitely distant stars should have had infinite time to reach us. Every line of sight should be filled with light that has been traveling forever. The sky should glow, but it does not. The paradox persisted because the models were incomplete. They treated space as a simple container, stars as eternal lamps, light as instantaneous. They did not yet see that time itself, the age of the universe, might be part of the answer. Philosophically, the question cut even deeper. If the universe is truly infinite and eternal, why does it look the way it does? Why darkness instead of light? Some thinkers turned to theology. An infinite, eternal universe might suggest no beginning, no creator, no first cause. That troubled many. Others wondered if the universe had a beginning after all. If it did, then distant light might not have had time to arrive. The darkness could be evidence of youth, of a finite past. These were quiet debates, held in letters, in observatories, in late-night conversations. They drove inquiry forward, not with urgency, but with patient persistence. One way people tried to feel the paradox was through simple thought experiments. Imagine a dark field at night. Place lanterns everywhere, as far as you can see, evenly spaced. If the field is infinite and the lanterns burn forever, every direction you look should be filled with light. No shadows, no dark patches. The whole field should glow. Now, suppose the lanterns are stars. The field is space. The same logic applies, yet the night sky is filled with dark patches between the lights. The lanterns are not infinite in number, or they have not burned forever, or something blocks the light. The simulation, simple as it is, brings the strangeness home. It was repeated in different forms throughout the 1700s and 1800s, sometimes with candles, sometimes with thoughts of glowing spheres. Each time, the same result. Logic says bright, reality says dark. The tension builds slowly. Astronomers counted more stars. By the early 1800s, estimates placed hundreds of millions of stars in the visible sky alone. More telescopes, better lenses, deeper catalogues. Still dark. Some suggested interstellar dust might absorb light, like fog dimming distant lamps. Others proposed the stars thin out at great distances, but observations showed no such thinning. The Milky Way. When mapped by William Herschel in the late 1700s, appeared as a vast disk, dense with stars, yet beyond it, darkness. The paradox refused to dissolve. It sat quietly in the background, a patient reminder that something fundamental was not yet understood. This tension, this gentle friction between expectation and observation, kept minds turning. It pushed people to measure more carefully, to question assumptions, to look again at the speed of light, at the age of things, at the nature of space itself. It prepared the way for the next steps, for Herschel's deep sky surveys, for parallax measurements, for the realization that galaxies lie far beyond our own, and eventually for the understanding that the universe is not eternal, not static, but young, expanding, still unfolding from a beginning. So let us rest here with the paradox. It is not a problem to be solved in haste. It is a quiet companion, a soft voice asking us to look longer, deeper, more patiently. The darkness we see tonight is not a flaw, it is a clue. And in the centuries that followed Diggers, that clue grew louder, not through shouting, but through stillness. Through the simple fact that the sky remains dark, even when logic says it should shine. We carry this quiet question forward now, into the next unfolding, into the deeper mapping, the first true measurements, the slow stretching of our understanding. We have carried the quiet paradox forward, the soft tension between infinite expectation and observed darkness. Now, let us move gently into a time when people began to look deeper, not just at the stars themselves, but at how they are arranged. The late 1700s, a period of calm persistence, when telescopes grew larger, mirrors brighter, and the night sky slowly revealed patterns no one had mapped before. At the center of this unfolding stood William Herschel, a man born in Hanover who moved to England in 1757, first as a musician, then as a composer, and finally as someone who could not look away from the stars. Herschel was not trained as an astronomer in the formal sense. He taught himself. In his spare time, he began building telescopes, not small spyglasses, but large reflectors. Using metal mirrors, he cast and polished himself. He experimented with different alloys, heated metals in a small furnace behind his house in Bath, poured molten speculum metal, cooled it, ground it, polished it hour after hour with his sister Caroline at his side. The Caroline Herschel, his devoted assistant, polished mirrors, recorded observations, catalogued comets, became one of the finest observers of her time. Together, they created instruments that gathered far more light than any before them. These telescopes allowed them to see fainter stars, deeper into the sky, farther than the eye alone could reach. Herschel's greatest contribution came not from discovering a single object, though he found Uranus in 1781, a new planet that expanded the known solar system. His deeper work was systematic, patient, almost meditative. He set out to map the stars, not just count them, but understand their distribution. He developed a method called stargazing, or star counting. He divided the visible sky into small sections, 683 zones in total, chosen carefully so they covered the heavens evenly. For each zone, he pointed his telescope, counted every star he could see down to a certain faintness, noted their brightness, their positions. Night after night, year after year, he and Caroline worked. They counted thousands upon thousands of stars. From these counts, Herschel built a picture. He found that the stars are not scattered uniformly in all directions. In some parts of the sky, toward the band we call the Milky Way, the stars crowd thickly. In other directions, perpendicular to that band, they thin out rapidly. The distribution suggested we live inside a vast flattened disk, a grindstone shape, with the sun near the center. The Milky Way, that pale glowing band across the sky, was not a cloud of distant vapor. It was the combined light of countless stars lying in the plane of our disk. Beyond the edges of this disk, the star density dropped sharply. Herschel drew a diagram, a cross-section view, showing the Sun embedded in a lens-shaped cloud of stars. For the first time, someone had attempted to sketch the shape of our home galaxy from within. It was a quiet revolution in perspective. We were no longer simply at the center of everything. We were embedded, off to one side perhaps, in a vast structure that had boundaries, though those boundaries were far away. Pause here. Breathe slowly. Feel how the view widens, gently. The universe no longer felt like a simple sphere around Earth. It began to feel like a place with structure, with depth, with layers. Herschel also turned his telescopes toward the mysterious cloud-like patches known as nebula. Some were bright, with clear shapes, rings, spirals. Others were faint, diffuse, almost ghostly. He catalogued hundreds. He wondered, quietly, whether some of these might be immense systems of stars, like our own Milky Way, but so distant they appeared as misty patches. Island universes, he called them in his notes, separate galaxies floating in the deep. He could not prove it. His telescopes were powerful, but not powerful enough to resolve individual stars in most nebulae. Still, the possibility lingered. The implication was profound. If some nebulae were distant galaxies, then the universe was far larger than the Milky Way disk. Our home, already vast, became just one among many. This idea, though not confirmed in his lifetime, planted a seed. It reduced the hold of geocentrism even further. We were not the center of a single enclosed cosmos. We were inside one galaxy, among perhaps countless others. Technologically, Herschel's work rested on optics. His large mirrors gathered more light, revealed fainter objects, allowed deeper penetration into space. Better reflectors meant better images. That improvement influenced many fields. Photography was emerging. Early daguerreotypes captured the moon, then stars. Precision grinding of mirrors, the patience required, carried over into other instruments, microscopes, surveying tools. The skill of building and using large telescopes quietly advanced engineering and craftsmanship. Psychologically, the shift was subtle but deep. The old Ptolemaic view placed humanity at the literal center, a position that carried comfort and meaning. Herschel's map, even though the Sun was still roughly central in his model, began to erode that centrality. We were inside a disk, not at the heart of everything. The stars were not fixed on a shell around us. They were distributed in depth, in layers, fading into distance. This expansion of perspective, this quiet realization that the cosmos has structure and scale far beyond our immediate surroundings, loosened the grip of the old enclosed model. It made room for later discoveries, for parallax measurements, for the proof that other galaxies exist, for the understanding that space itself expands. Herschel did not solve the dark sky paradox, but he changed the context in which it was asked. If the stars cluster in a disk, thin out outside it, then perhaps the infinite uniform distribution assumed in the paradox does not hold. Perhaps the universe is not filled evenly forever. Perhaps there are edges, or at least strong gradients. His work, patient and systematic, prepared the ground. It showed that careful counting, repeated observation, could reveal patterns invisible to the casual glance. So let us rest here with the image of that great disk, the Sun embedded within it, the Milky Way as the bright plane of our home, and beyond, faint nebulae hinting at more. The sky has grown deeper, the darkness between the stars, no longer just an absence, begins to feel like distance, like depth, like space stretching away. And in that stretching, the next steps wait quietly. The first measurements of true distance, the proof of worlds beyond our own, the slow unfolding of expansion and beginning. We carry this wider view forward now, gently, without hurry. We have mapped the stars, felt their distribution in quiet layers, seen the hints of nebulae whispering of deeper spaces. Now, let us turn, gently, to the challenge that lay beyond mapping. The challenge of distance, for all the counting, all the cataloguing. The stars remain points of light. How far were they? Without knowing distance, the cosmos stayed flat, like a painting on a wall. Depth, true depth, required measurement. And in the 19th century, patient minds began to find ways. The first method, simple in concept, profound in execution, was stellar parallax. It was pioneered by Friedrich Bessel, a German astronomer, in the 1830s. Bessel did not invent parallax. The idea had been around since ancient times, but he was the first to measure it in the stars. Parallax is the apparent shift of a nearby object against a distant background when you change your viewpoint. It is how our eyes judge depth in daily life. Hold out your finger. Close one eye, then the other. The finger seems to jump against the wall behind it. The closer the finger, the bigger the jump. Now apply this to the stars. The Earth orbits the Sun, moving from one side of its path to the other over 6 months. That is a baseline of about 300 million kilometers. 2 viewpoints separated by the diameter of our orbit. If a star is relatively close, it should appear to shift slightly against the more distant stars. Measure that tiny shift, and trigonometry tells you the distance. Trigonometry, the quiet mathematics of angles and triangles. The shift angle, called the parallax angle, is half the apparent movement over the year. The distance in parsecs, a unit named for parallax of 1 arcsecond, is simply 1 over that angle in arcseconds. An arcsecond is tiny, 1/36th of a degree. For even the nearest stars, the shift is minuscule, less than the width of a human hair seen from across a room. Bessel chose a star called 61 Cygni, known for its fast, proper motion, suggesting it was close. He observed it meticulously over many months, using a precise instrument called a heliometer, a split-lens telescope that measured small angles. In 1838, he announced the result. 61 Cygni was about 10 light-years away, 10 trillion kilometers. For the first time, a star's distance was measured, not guessed. Pause here. Let that sink in. A number attached to the vastness. What had been speculation became measurement. The mechanism is pure trigonometry. Imagine a triangle. The base is Earth's orbit diameter. The 2 long sides point to the star from opposite sides of the orbit. The parallax angle is at the star's vertex. Simple ratios give the distance, but the angles were so small, instruments had to be exquisite. Atmospheric turbulence, twinkling, blurred measurements. Bessel averaged hundreds of observations, corrected for errors. Patiently, his work opened the door. Soon, others measured more stars. By the end of the 19th century, a few dozen had known distances, but parallax had limits. The baseline, Earth's orbit was fixed. For stars beyond a few hundred light-years, the shift became too small to detect. The method confined us to our local neighborhood. The vast Milky Way, the nebulae, remained unmapped in depth. We needed a longer ruler, something to extend our reach. That something came from an unexpected place, from the patient work of Henrietta Leavitt at the Harvard College Observatory in the early 1900s. Leavitt was one of the computers women hired to catalog stars from photographic plates. Her job was meticulous, measuring brightness, positions from glass plates exposed at telescopes around the world. But Leavitt saw patterns. She focused on a class of stars called Cepheid variables. These stars pulse, brighten, and dim over days or weeks. Their light varies rhythmically. Leavitt studied them in the Small Magellanic Cloud, a faint companion to our Milky Way, visible in the southern sky. She measured 25 Cepheids there, and she found a quiet pattern. The brighter the Cepheid, the longer its period of pulsing. A star that took longer to cycle bright to dim was intrinsically brighter. This was the key. If all these Cepheids were at roughly the same distance, in the same cloud, then the pattern linked period to true luminosity. Measure the period, easy from the light curve, and you know how bright the star really is. Then, observe how bright it appears from Earth. Dimmer due to distance. The difference tells you how far away it is. Leavitt had found a standard candle, a star whose true brightness you could calibrate from its pulse, like knowing a lantern's wattage, then judging distance from how faint it looks. The mechanism is inverse square law. Light spreads out, intensity falls with the square of distance. Apparent brightness equals true brightness divided by distance squared. Solve for distance. But first, calibrate the relation. Leavitt's period luminosity law, as it became known, was the ruler we needed. It extended beyond parallax. Cepheids are bright, visible far away. Find one in a distant cluster or nebula, measure its period, apparent brightness, and compute distance. The empowerment was profound. What had been speculation is that nebula close or far became measurement. Distances to star clusters, to the edges of the Milky Way, suddenly possible, and beyond. In the early 1920s, Edwin Hubble used Leavitt's relation at the Hooker telescope on Mount Wilson. He spotted Cepheids in the Andromeda Nebula, measured their periods, their faintness, calculated over 2 million light-years away, far beyond the Milky Way. Andromeda was not a nebula, it was a galaxy, like ours. The universe grew immense. Modern refinements have sharpened these tools. Space telescopes like Gaia, launched in 2013, measure parallax for billions of stars, out to thousands of light-years, accuracy down to micro-arcseconds. For Cepheids, the Hubble Space Telescope and now James Webb recalibrate the period luminosity law, using nearby Cepheids with parallax distances, the constant refined. Distances to galaxies now reach billions of light-years. The empowerment continues, from guesswork to precision. The dark sky's mystery edges closer to resolution. But for now, in this chapter, we rest with the quiet triumph of measurement. The stars, once unreachable, now have distances attached. We carry this deeper reach forward to the revelations of expansion, curvature, beginning. We have measured distances now, reached across light years with parallax and Cepheid candles, seen that Andromeda lies far beyond our Milky Way, an island of stars in its own right. The universe has grown vast, yet the darkness still lingers, patient, waiting for its full explanation. In the 1920s, a quiet convergence began. Two separate threads, observation and theory, came together, slowly, almost inevitably, to reveal that space itself is not still. It moves, it stretches. The man at the center of the observational thread was Edwin Hubble. Hubble worked at the Mount Wilson Observatory, high above Los Angeles, home to the Hooker telescope, the largest in the world at that time. A 100-inch reflector capable of gathering light from immense distances. Hubble was determined, methodical, sometimes brusque, but deeply skilled. He had already used Henrietta Leavitt's period luminosity relation to prove that Andromeda was not a nebula inside our galaxy, but a separate system over 2 million light-years away. That proof alone pushed the boundaries outward. But Hubble did not stop there. He turned his telescope to other spiral nebulae, faint patches once thought to be gas clouds. He searched for Cepheid variables within them. One by one, he found them. Measured periods, apparent brightnesses, calculated distances. Each time, the numbers came back enormous. These were not nearby clouds. They were galaxies, separate, distant, each containing billions of stars. The universe was not one galaxy with some misty patches. It was filled with galaxies, scattered through space, like islands in an ocean. Hubble catalogued them, measured redshifts. Redshift, the key that unlocked the next layer. When light travels from a distant source, if that source is moving away from us, the light waves stretch. Wavelengths grow longer. Blue light shifts toward red, green toward yellow. The entire spectrum slides to longer wavelengths. This is the Doppler effect, the same principle that makes a siren pitch drop as an ambulance passes and moves away. Hubble observed the spectra of distant galaxies. Their absorption lines, the dark gaps where atoms absorb specific wavelengths, were shifted toward the red end. Every distant galaxy showed redshift, and the farther away, the greater the shift. The pattern was clear, linear. Distance doubled, redshift doubled. Hubble plotted the data. Distance on one axis, velocity inferred from redshift on the other. A straight line emerged with positive slope. The slope became known as Hubble's constant. The implication was startling. The galaxies were not just distant, they were receding from us, all of them, in every direction. The farther away, the faster they moved away. This was not us at the center of an explosion, with everything fleeing outward from Earth. That would violate the Copernican principle, the idea that we occupy no special place. Instead, the observations fit something more profound. Space itself was expanding. Imagine a balloon, not fully inflated. Draw dots on its surface, representing galaxies. Now inflate the balloon slowly. Every dot moves away from every other dot. The farther apart two dots are, the faster they separate, because more rubber stretches between them. No dot is the center. The expansion is of the surface itself. Galaxies are not flying through space like shrapnel. The space between them is stretching. Light traveling from one galaxy to another through that stretching space has its wavelength stretched along the way. Redshift is the signature of expansion. Hubble published his findings in 1929. The paper was short, understated, but the impact was immense. The universe was dynamic, not static. This brought the observational thread into contact with another, one that had been developing quietly in the realm of pure thought. Albert Einstein, in 1915, had completed general relativity, a theory of gravity not as a force, but as curvature of space and time. Mass and energy bend the fabric. Objects follow the straightest possible paths, geodesics in that curved geometry. Our planet's orbit, not because of invisible pulls, but because space is warped around the sun. The equations of general relativity apply to the universe as a whole. In the 1920s, cosmologists began to explore solutions describing the entire cosmos. Most assumed, following Newton and common intuition, that the universe was static, unchanging on the largest scales. Einstein himself believed this. To make his equations yield a static universe, he introduced a term called the cosmological constant, a kind of repulsive energy balancing gravity. A fudge factor, he later called it. But in 1922, a Russian mathematician, Alexander Friedmann, found solutions where the universe expands or contracts. No need for the constant. The equations naturally allowed dynamic universes. Belgian priest and physicist Georges Lemaitre, independently, derived similar expanding models in 1927. He even suggested the universe began from a primeval atom, a hot, dense state, expanding outward. When Hubble's data appeared, the match was clear. The observed recession velocities fit the predictions of expanding models. Einstein visited Hubble at Mount Wilson, saw the plates, the redshifts. He accepted the evidence. The cosmological constant, he later said, was his greatest blunder. Though today, we know it may not have been a blunder after all. But that is for later. In the 1920s, the unification happened. Observation, Hubble's redshifts and distances met theory, relativity's dynamic solutions. Space expands. The universe has a history. It is getting larger. The darkness, the paradox, begins to find its answer. In an infinite static universe, light from everywhere should fill the sky. But if the universe began finite in time, then light from the farthest regions has not yet reached us. There is a horizon, a distance beyond which light has not had time to travel since the beginning. Only the light that has had 13.8 billion years, or whatever the precise age turns out to be, can reach us. Beyond that, darkness, because the journey is unfinished. The observable universe is finite, not because space ends, but because time began. Pause here, let the thought settle. The balloon illustration helps. Draw dots, inflate slowly, the surface grows, distances increase, light traveling from one dot to another gets stretched. If you start the balloon from a tiny point and inflate for a finite time, distant dots are beyond the reach of light that started at the beginning. Only nearby dots send light that has arrived. The rest remain unseen. Dark. This unification, observation and theory coming together, was quiet but complete. No drama, just data-fitting equations, patterns aligning. The 1920s closed with the universe no longer static, no longer eternal in the past. It had a beginning, or at least a very early hot phase, and it was expanding. The darkness between the stars, no longer a puzzle without shape. It had context, it had depth, it had time. We rest here with this gentle revelation. The sky is dark because the universe is young, because space stretches, because light takes time. The next steps wait quietly. The curvature of space, the relic glow from the beginning, the final resolution of the paradox. We carry this expanding view forward, softly, without haste. We have watched the universe expand, seen galaxies drift apart, felt the gentle stretching of space itself. The darkness between the stars begins to speak of time, of a finite beginning. But to understand how that expansion can happen at all, how matter and energy move across such vast reaches, we must look more closely at the nature of space, not as a flat, empty stage, but as something that can bend, respond, curve. The idea that space is not rigid, that it can take shape, emerged quietly in the 19th century. It began with Carl Friedrich Gauss. Born in 1777 in a modest home in Brunswick, Gauss was one of those rare minds who saw deeper into the foundations of mathematics than almost anyone before him. From childhood, he questioned the axioms of geometry laid down by Euclid more than 2,000 years earlier. Euclid had assumed that parallel lines never meet, that the angles in any triangle always sum to exactly 180 degrees. That space is flat, uniform, infinite in a straight and simple way. Gauss wondered, in private notes he rarely published, whether other possibilities existed. He explored curved surfaces, like the surface of a sphere. On a sphere, parallel lines do not stay parallel. Meridians starting from the equator converge at the poles. Triangles drawn on the surface have angles that add to more than 180 degrees. Nor a triangle from the North Pole down to the equator, along the equator for a quarter of the way, back up to the pole, has 3 right angles, 270 degrees total. The rules change. Gauss developed a way to measure this curvature from within the surface, without ever needing to step outside into a higher dimension. He called his insight the Theorema Egregium, the remarkable theorem. Curvature is intrinsic. It can be detected by creatures living on the surface, by measuring angles, distances, small paths. No external viewpoint required. This was the first quiet step toward non-Euclidean geometry. Gauss shared these thoughts sparingly, mostly in letters, but the seed was planted. His student, Bernhard Riemann, carried it further. In 1854, at the age of 28, Riemann delivered a lecture in Göttingen titled "On the Hypotheses Which Lie at the Foundations of Geometry." In it, he generalized the idea to spaces of any dimension. He introduced the concept of a metric tensor, a mathematical object that, at every point in space, specifies how to measure infinitesimal distances. Think of it as a local ruler, a small set of numbers that define length, angle, volume, in a possibly curved region. The metric tensor allows you to compute distances along any path, even when the space bends. Riemann showed that geometry could be defined entirely from within, using this tensor. Curvature becomes a property of the manifold itself, not something imposed from outside. He described spaces where parallel lines diverge, hyperbolic geometry, and spaces where they converge, elliptic geometry. These were abstract, beautiful, pure mathematics. No one yet imagined they described the real world, but the possibility existed. Space could be curved. Pause here, just breathe. Let the thought settle. The flat plane of Euclid, the straight lines we draw on paper, the right angles of a room are special cases. local approximations, at cosmic scales, space might behave differently. Now, in the early 20th century, Albert Einstein brought these mathematical ideas into physics. Einstein had already revolutionized our view of space and time with special relativity in 1905, showing that space and time are interwoven, that simultaneity is relative, that nothing exceeds the speed of light. But gravity remained a puzzle. Newton described it as an instantaneous force acting across empty space. Einstein disliked action at a distance. He sought a geometric explanation. In November 1907, while working at the patent office in Bern, he had what he later called his happiest thought. A person falling freely feels no gravity. In a closed elevator in free fall, you float weightless. Acceleration and gravity are indistinguishable locally. This equivalence principle became the foundation. If gravity is equivalent to acceleration, and acceleration curves paths, then gravity must curve paths. By 1915, after years of intense work, Einstein completed the general theory of relativity. Gravity is the curvature of space-time caused by mass and energy. The four-dimensional fabric of space-time warps around a massive object. Planets, stars. Follow geodesics, the straightest possible paths in this curved geometry. No force pulls them. They simply move along the curves created by the presence of mass. The equations are compact, 10 nonlinear partial differential equations, but they describe everything. The metric tensor, Riemann's tool, becomes dynamic. It changes from point to point, shaped by the distribution of matter and energy. Solve for the metric, trace the geodesics, predict orbits, light paths, time dilation. Gravity demystified. No invisible strings reaching across emptiness, just the shape of space-time guiding motion. To test it, Einstein predicted that light passing near the sun would bend. In Newtonian gravity, light has no mass, so no deflection. But in general relativity, light follows null geodesics, curved by the warped space. At the predicted deflection, 1.75 arc-seconds for light grazing the solar limb, twice the Newtonian value. The test came during the total solar eclipse of May 29, 1919. Two British expeditions, one to Sobral in Brazil, led by Andrew Crommelin, the other to Principe Island off West Africa, led by Arthur Eddington. They photographed the star field near the eclipsed sun, compared the positions to photographs taken months earlier when the sun was elsewhere in the sky. The stars appeared shifted outward, away from the sun, by almost exactly the amount Einstein predicted. The light had bent. Announcements followed in November 1919. Newspapers proclaimed a revolution. Revolution in Science read one headline: New Theory of the Universe, Newtonian Ideas Overthrown. Einstein became known worldwide. The confirmation was quiet in its precision, dramatic in its implication. Gravity is geometry. Forces become paths in curved space-time. This curved view integrated perfectly with the expanding universe. Friedmann's and Lemaitre's solutions to Einstein's equations described dynamic cosmologies, universes that expand from a dense origin. The cosmological constant Einstein had added to force a static universe turned out unnecessary. He later called it his greatest blunder, though modern cosmology has revived a similar term for dark energy. For now, in the 1920s and beyond, general relativity provided the framework. Space-time curves, expands, carries the galaxies apart. The darkness between them, the vast reaches, is not empty nothingness. It is curved, stretching, shaped by the total matter and energy within it. It responds to what is there, and in responding, it guides light, time, motion. We rest here with this quiet beauty. Space is not a passive container. It is alive to presence, flexible, geometric. The force we once called gravity, demystified, becomes the gentle curve of the cosmos. The next steps wait patiently. The relic radiation from the beginning, the full tying together of expansion, curvature, origin. We carry this curved understanding forward, softly, into the light that still echoes from the dawn. We have curved space now, felt its gentle warp under the presence of mass, watched galaxies drift apart in an expanding fabric. The darkness between them begins to carry meaning, not as absence, but as distance stretched by time. If the universe is expanding today, then running time backward brings everything closer. Closer, hotter, denser. Eventually, to a single point of unimaginable heat and density. A beginning. This idea, the hot origin of the cosmos, emerged slowly in the 20th century. It was not born in a flash of inspiration, but through patient mathematics, unexpected observations, and the quiet alignment of theory with evidence. The link is straightforward when you let it unfold. Expansion means distances grow with time. Rewind the clock, distances shrink. The farther back you go, the smaller the observable universe becomes. Matter and energy pack into smaller volumes. Temperature rises. In the very early stages, the cosmos was a sea of radiation, particles moving near the speed of light, too hot for atoms to form. As expansion continued, cooling occurred. About 380,000 years after the beginning, the temperature dropped below roughly 3,000 Kelvin. Electrons combined with protons to form neutral hydrogen atoms. Before that moment, the universe was opaque. Light scattered endlessly by free electrons. After, it became transparent. The radiation that had been trapped suddenly streamed freely in all directions. That primordial light, the glow from the moment the cosmos cleared, has been traveling ever since. And because space itself has been stretching for billions of years, that light has stretched with it. Wavelengths lengthen. What began as visible and ultraviolet light shifted through infrared into the microwave part of the spectrum. The temperature cooled from thousands of degrees to just 2.725 Kelvin today. A faint, uniform, all-sky glow, invisible to the eye, but detectable with radio receivers. This is the cosmic microwave background, the CMB, the afterglow of creation. Its existence was first predicted theoretically. In the 1940s, George Gamow, Ralph Alpha, and Robert Herman, working on the hot Big Bang model, calculated that relic radiation should remain. They estimated a temperature around 5 Kelvin, a quiet prediction, published, then largely forgotten. Decades later, in the early 1960s, Robert Dick at Princeton revived the idea. He reasoned that if the universe had a hot, dense phase, the radiation should still fill space. Isotropic. Black body in spectrum. Dicker and his group, James Peebles, Peter Roll, David Wilkinson, began building a detector to search for it. At the same time, quite by accident, two engineers at Bell Laboratories in Holmdel, New Jersey, stumbled upon it. Arno Penzias and Robert Wilson were using a large horn-shaped antenna originally built for satellite communication tests. They were calibrating it for radio astronomy. They found a persistent, low-level noise, a hiss that appeared no matter which direction they pointed the antenna. It did not vary with time of day, season, or weather. They ruled out local sources, terrestrial interference, even pigeon droppings inside the horn. The noise remained, a steady, uniform, microwave signal from every part of the sky. When Penzias mentioned it to a colleague, the connection was made. He called Dicke. Dicke immediately recognized what it was. The hiss was the predicted relic radiation. Penzias and Wilson measured its temperature, about 3.5 Kelvin at first, later refined to 2.725 Kelvin. The spectrum matched a perfect blackbody, exactly as expected from a hot, expanding origin. They published their discovery in 1965 in the Astrophysical Journal, a short, modest paper. The title simply, "A Measurement of Excess Antenna Temperature at 4080 MHz. No grand claims, but the implication was profound. The CMB provided direct evidence of the hot Big Bang. Tiny temperature fluctuations, later mapped with exquisite precision by satellites COBE in 1992, WMAP in 2001, Planck in 2013, show variations of about 1 part in 100,000. These ripples, quantum seeds amplified by gravity, grew into the galaxies and clusters we see today. The pattern matches predictions, confirming the model. Now pause. Breathe slowly. Let the thought rest. So the CMB resolves the oldest part of the dark sky puzzle. In an infinite, eternal, static universe, light from every direction, every distance, should have reached us long ago. The sky should be bright, saturated with overlapping starlight. But if the universe has a finite age, then light from the most distant regions has simply not had time to arrive. There is a cosmic light travel horizon. The observable universe is the sphere around us, with radius equal to the distance light has traveled since the beginning. About 13.8 billion years ago. Because of expansion, that sphere is now roughly 46.5 billion light-years in radius. The observable diameter, nearly 93 billion light-years. Beyond that horizon, light is still on its way, but it has not yet reached us. The sky remains dark in those directions, not because there is nothing there, but because the journey is unfinished. The CMB itself marks the farthest we can see directly, the surface of last scattering, when the universe became transparent. Light from before that time is trapped, scattered, never free to travel. The darkness, then, is the shadow cast by time itself. Not emptiness, not failure of light. Simply distance in time. We rest here with this quiet resolution. The hiss in the antenna, the uniform glow mapped across the sky, the tiny ripples that seeded everything we know. The universe had a beginning, expanded from heat and density, cooled, cleared, and the light from that dawn still fills every corner. Stretched thin, cool, but present. The paradox of infinite darkness, after centuries of patient questioning, finds its gentle answer. Not in infinity, but in finitude. Not in eternity, but in a single moment long ago, when everything began to unfold. We carry this origin story forward, softly, into the final reflections, the echoes that linger in our own quiet nights. We have traveled far, slowly, through centuries of quiet questioning. From the first bright anomaly in 1572 that cracked the fixed shell, through infinite space and its stubborn paradox, through the patient mapping of our galaxy. The first true measurements of distance, the revelation that space expands, the bending of geometry under gravity, and the faint microwave glow that still echoes from the beginning. Now, in this final chapter of the unfolding, all the threads draw together. The darkness we see every night, the simple black between the stars, is no longer a mystery without shape. It is the gentle signature of a universe with a finite age. Let us rest here and let the pieces settle into place. The core resolution is straightforward, yet profound when you allow it to sink in. If the universe had existed forever and were truly infinite and filled with stars in every direction, then every line of sight would end on the surface of a star. Light from those stars, having had infinite time to travel, would fill the sky completely. The night would be bright, glowing uniformly, like standing inside an immense furnace. But the night is dark. The only consistent explanation is that the light from the most distant stars has simply not had time to reach us. The universe has not existed forever. It began at a definite moment, approximately 13.8 billion years ago. That beginning sets a hard limit on how far light can have traveled. Light moves at a finite speed, about 300,000 kilometers per second. In 13.8 billion years, it can cross a distance of 13.8 billion light years. Because of expansion, the actual size of the observable universe is larger, roughly 93 billion light years across. The light we receive today from the farthest objects left them when the universe was much younger, and those objects have since moved farther away as space stretched. Yet the key point remains. There is a cosmic horizon. Beyond that horizon, light is still traveling toward us, but it has not yet arrived. The regions beyond remain unseen, dark. The observable universe, the part from which light has reached us, is therefore finite. Not because space itself ends, but because time had a start. The darkness is the shadow cast by the finite history of everything. It is not an absence of stars or galaxies. It is an absence of time enough for their light to arrive. This finite age caps the visible light in an eternal universe. Infinite past, infinite light travel time, infinite accumulation. In our universe, finite past, finite travel time, finite accumulation. Only the light that has had 13.8 billion years, or less, depending on how far back the source is, can contribute to what we see. The rest waits in the dark. Expansion mechanics make this even clearer. As space stretches, the distance between any 2 points increases over time. Light traveling toward us must cross an ever-growing path. For very distant sources, the expansion can outpace the light, so some light never reaches us at all. This is the cosmic event horizon, but even without that, the age limit alone suffices to explain the darkness. The proof of the Big Bang lies, in part, in this very darkness. The night sky is not bright because the universe is young, because it had a beginning, because expansion has stretched the oldest light into invisibility or microwaves. The CMB itself is one piece of that oldest light, stretched from the moment of transparency. But the darkness between the stars and galaxies, the black we see with our eyes, is the complementary evidence. It shows that not all possible light has arrived. The observable universe is bounded by time, not by an edge of space. We live inside a sphere of light that has had time to reach us, surrounded by darkness that has not yet spoken. Pause here. Just breathe. Let your eyes rest on the night sky if it is near you, or imagine it. The stars you see, their light left long ago, some before humans walked, some before the first cities rose. But between them, the dark is not empty. It is waiting. It is the part of the story still on its way. This integration ties every earlier step together. Digger's infinite space, Olbers Paradox, Herschel's disk, parallax and Cepheids, Hubble's recession, Einstein's curvature, the CMB glow, all converge on one quiet truth. The universe is not eternal in the past. It began, it expands, it cools. And because of that finite beginning, the sky at night is dark. The paradox, after 4 centuries of patient circling, is resolved. Not with a dramatic flourish, but with the simple recognition that time had a start and light takes time. The darkness we have gazed at since childhood, the darkness that once seemed ordinary, now carries the deepest message. It tells us the cosmos is finite in age, dynamic in nature, still unfolding. It is proof, silent and steady, of a beginning. We rest here with the full picture settled. The night sky, dark between the lights, is no longer a puzzle. It is an answer, a gentle, profound, patient answer. And so, as we close this chapter of discoveries, we turn softly toward what these revelations mean beyond the equations and telescopes, toward the echoes in society, in philosophy, in the quiet way we now see ourselves and our place. The after, the long reach of these truths into our own time, and perhaps into whatever future still lies ahead. We carry this resolved darkness forward into reflection without hurry. We have followed the quiet path of discovery, from the first crack in the fixed shell, through paradox and measurement, to the curved fabric of space-time and the faint microwave echo of the beginning. The darkness between the stars, once ordinary, now carries the weight of a finite age, of expansion, of a universe that had a start. These revelations did not remain locked in observatories or equations. They flowed outward, gently, reshaping how societies organize, how technologies serve daily life, how human beings see themselves against the vastness. Let us rest here and trace those ripples, slowly. The most visible societal echo came in the middle of the 20th century with the space programs. The understanding that we live in a vast, expanding cosmos inspired governments and peoples to reach outward. The Apollo missions, landing humans on the moon in 1969, were not only feats of engineering, they were expressions of a new perspective. We had learned the Earth was not the center, not even the center of our own galaxy. The pale blue dot, photographed from lunar orbit, became a quiet symbol. Humanity, small, fragile, yet capable of looking up and traveling toward what we see. The Cold War rivalry between the United States and the Soviet Union turned space into a shared frontier. After Apollo, cooperation grew. The International Space Station, orbiting since 1998, involves agencies from 15 nations, a continuous human presence in space, sustained by partnership. The Hubble Space Telescope, launched in 1990, refined the expansion rate, measured distances to distant galaxies with unprecedented clarity, and produced images that entered public consciousness. The deep fields, tiny patches of sky revealing thousands of galaxies, reminded billions that the universe is not empty, but filled with worlds beyond counting. These efforts fostered a sense of shared wonder, a recognition that the questions we ask about the cosmos belong to all of us. Technologically, the revelations bore fruit in everyday tools. General relativity, once abstract, now corrects the time signals in GPS satellites, without accounting for the weaker gravity in orbit and the effects of velocity. Clocks on satellites would drift, positioning errors would accumulate by kilometers each day. Relativity keeps your phone's map accurate. The study of the cosmic microwave background, the relic radiation from the early universe. Advanced particle physics and detector technologies. The same precision needed to map tiny temperature fluctuations in the CMB. 1 part in 100,000 helped develop ultra-sensitive instruments used in medical imaging, materials, science, quantum computing research. The pursuit of cosmic answers quietly improved life closer to home. Perhaps the deepest shift occurred in human self-perception. For millennia, cosmological models placed humanity at or near the center, a position that carried comfort, purpose, a sense of cosmic importance. The journey we have followed, Copernicus moving Earth from the center, Herschel embedding us in a disk, Hubble showing countless galaxies, Einstein curving space-time, steadily removed that centrality. We are not the fixed point around which everything turns. We occupy an ordinary position in an ordinary galaxy, one among perhaps 2 trillion. This demotion, this quiet displacement, brought humility. It countered anthropocentrism, the assumption that the universe was made for us or revolves around us. In its place grew a different awe, not pride of place, but wonder at our ability to understand a cosmos so much larger than ourselves. The darkness that once seemed indifferent now feels like evidence of shared history, of a beginning we all emerged from. Looking ahead, the long-term fate of the cosmos carries its own contemplative weight. In the late 1990s, observations of distant supernova showed that expansion is accelerating, not slowing under gravity as once expected, but speeding up. A mysterious repulsive effect, now called dark energy, dominates. If this acceleration continues, distant galaxies will recede faster and faster. Their light will redshift beyond detection. One by one, they will fade from view. In trillions of years, observers in what remains of our local group, the galaxies gravitationally bound to the Milky Way, will see an empty sky. Only the stars within our merged local cluster will be visible. The rest of the universe hidden behind an ever-growing horizon. Future civilizations, if any exist, will have no evidence of other galaxies. The CMB will have cooled further, stretched to longer wavelengths, nearly undetectable. The observable universe will shrink in practical terms. This cosmic isolation, far in the future, echoes the humility we feel today. It reminds us that even our current view, rich with galaxies, is temporary. The darkness we see tonight already hides much. In time, it will hide more. Yet this fate also parallels closer concerns. The universe evolves, expands, cools, moves toward greater entropy. Earth's resources, finite, follow similar limits. Understanding cosmic evolution quietly reinforces the need for stewardship, for sustainability. A species that grasps the finite age of everything, the stretching of space, the eventual dimming, may feel a deeper responsibility toward its own small, temporary home. Post-1920s, cosmology influenced philosophy profoundly. Existential questions. Why is there something rather than nothing? Found new context. The evidence of a beginning, a hot, dense origin, reduced some forms of existential dread. The universe is not an eternal, meaningless void. It has a narrative, a direction, from singularity to structure to expansion. Even if the ultimate fate is isolation, the fact that we exist, that we can know this story, carries its own quiet meaning. We rest here with these enduring effects. The revelations reshaped cooperation, technology, humility, our sense of time and place. They continue to echo in satellites orbiting overhead, in images from distant telescopes, in the philosophical stillness that comes when we look up at night. The story does not end. It simply widens, softens, invites us to carry the wonder forward. So let us turn, gently, to a final synthesis, to gather the threads, reflect on the arc, and leave with one open, quiet question. Word count, approximately 1,520, paced for slow, the reflective narration with natural pauses, totaling 2 to 3 minutes of breathing room and ambient silence within the section. 5. Synthesis and conclusion. We began under a simple night sky with the familiar darkness between the stars. A darkness most accept without question. Yet that darkness, patient and unassuming, became the thread that guided us through centuries. We started with ancient models, comforting enclosed shells. Earth at the center, stars fixed on a sphere. Space flat and familiar, vacuum unthinkable, humanity meaningfully placed. Then came the first cracks. The supernova of 1572, a new light where none should appear, leading diggers to scatter the stars into infinity. With infinity, the paradox arrived. If endless stars in endless space, why dark? Line of sight should fill with light. The sky should glow. But it does not. There the tension lingered through Herschel's patient counting, revealing our galaxy as a vast disk, through parallax and Cepheids, giving true distances, through Hubble's redshifts, showing expansion, through Einstein's curvature, turning gravity into geometry, through the microwave background, the cooled glow from the beginning. Each step, quiet, interconnected, built on the last. Paradoxes drove progress, not by shouting, but by refusing to dissolve. Curvature and expansion resolve them, showing space bends, stretches, carries a memory of origin. The nothing between the stars, once mere emptiness, revealed itself as temporal, shaped by time, by distance light has not yet crossed, by a universe with a finite age. The dark sky is proof of a beginning. 13.8 billion years ago, everything emerged from a hot, dense state, expanded, cooled, formed atoms, released light, and that light, stretched by expansion, still fills space as a faint microwave hum. The darkness we see with our eyes is the part beyond that light's reach, the horizon set by time itself. This journey, from enclosed comfort to vast humility, reshaped more than astronomy. It reshaped how we cooperate, how we build tools, how we understand our smallness, our brief moment in the story, and it points ahead. Dark energy accelerates the expansion. Galaxies recede faster, their light redshifts beyond visibility. In the deep future, observers will see fewer and fewer galaxies, until only our local group remains, surrounded by growing darkness. The observable universe, already limited by time, will shrink in practical reach. What does this mean? For us today, it is a reminder. The view we have now, rich with galaxies, is temporary. The darkness that surrounds us will one day surround others even more. Yet, in this very temporality, there is quiet beauty. We exist at a moment when the sky is still full enough to wonder at, when we can map the CMB, measure expansion, trace curvature, know the beginning. We are witnesses, brief but awake. So let us end, not with finality, but with one gentle question. As expansion continues, as more of the universe slips behind the horizon, what might we understand next when we look up again in the quiet of night? What new darkness, what new light waits for those who come after? The sky tonight, dark between the stars, holds no answer, only invitation to pause, to breathe, to wonder. And in that wonder, to feel, for a moment, part of something immense, unfolding, still.